Okay, I'm sitting here in a little rock shelter cave in the Patapsco River Valley State Park on the county line between Baltimore County and Howard County. The rock here itself is a schist containing lots of mica, both black and white mica. The white mica is muscovite, and black mica is called biotite. The rock itself, since it is cooked to a medium well done, means that all the original characteristics of the rock, or most of them, have been destroyed. The original texture and structure are gone. So how do we tell what kind of rock this was originally? One way to do it, in fact about the only way to do it, is to look at the chemical composition of the rock. What minerals are in it and what is the chemistry? It turns out that it's a very aluminum-rich rock. Micas are aluminum-rich. Feldspar, which is also in here, is aluminum-rich, and it also contains quartz, which is silica-rich. So this was made mostly of silicon and aluminum with a little bit of iron in it to give you the black mica. Now, what kind of rock would that have been originally? With all the aluminum in it, almost certainly that marks it as a rock that originally was very clay-rich. This was a clay-rich mud to start with, many millions of years ago. Now there are many different places where that can be deposited. The rock immediately underlying this, it turns out, we'll take a look at it later, is a marble. That was limestone. Limestone is generally characteristic of a tropical, warm ocean without much going on, without much junk being carried in, because it's mostly made up of seashells, living animals and plants that have pulled calcium carbonate out of the water. Underneath that is a almost pure quartz rock, the setter's quartzite. That was probably a sand beach. Not pure sand, there is other stuff in it too, but mostly sand. Below that is a billion-year-old gneiss, which was originally a granite. Now, where would you find such a rock today? Well, this originally was an ancient landmass formed 1 billion years ago, which had the ocean come in over it, so it was eroded away, eroded flat, actually down to and below sea level. A beach came in over it, that's the sand. Then when it sank a little bit further, or sea level rose a little bit more, you had a nice tropical ocean. That's the limestone. Followed by mud being washed in from mountains going up far away, because it's a very fine mud. There is mud being deposited today in the Mississippi River Delta. No nearby mountains. It's being carried from thousands of miles away. Presumably the same here. That's the bet we've got. Okay. We find rocks like that in western Maryland where we can put a good date on them. The rocks in western Maryland are dated about 500 million years ago, and the geological setting was very much like that of the Gulf Coast or coast of Carolina today. Geologically very quiet. Nothing like California, the West Coast, or Indonesia, or places like that that are geologically active. Now this is interesting because the surrounding rocks near this area are from a very geologically active environment with lots of igneous activity, lots of faulting, earthquakes, mountains, California. So what is this chunk of rock doing here? Well, it turns out that the rocks that have all that geological activity, such as in Western Regional Park or down along the Potomac River just upstream from Washington, those rocks are not, strictly speaking, deposited in North America. They were deposited on the other side of an ocean and have only been added to North America more recently. Funny thing about those kinds of rocks, though, they're found on both sides of this chunk of rock. So how did this chunk of rock get here? Well, the present theory, if you can come up with a better one, you're welcome to. The present theory is that this is a chunk of North America that broke off and drifted away 700 or 800 million years ago. very much like Madagascar off the west coast of Africa, which was originally a part of the mainland, which broke off, moved out a couple of 100 miles, and then stopped, didn't go any further. So this did the same thing. And in the intervening ocean in between, we deposited deep ocean rocks, and on the other side, we deposited deep ocean rocks. On the other side of the ocean altogether was Africa and Europe, and the ocean on that side started closing between 500 and 600 million years ago, very much as the Pacific Ocean is closing up today off the west coast of Washington, Oregon, and Northern California. Okay, well, this is the same rock just a few feet away from where we saw the cave. In this particular spot, though, it's got an awful lot of interesting light-colored structures here. These are actually veins of granite that have come in through here. So at the time that this was being cooked, part of the reason it was being cooked is because there was granite being intruded around here. In this particular case, all the light-colored veins here are granite, and they were intruded in between the layers of metamorphic rock. Also, you can see that they are extremely deformed. In some cases, they wind around, zigzag back and forth. That's given a special name that's called pigmatic folding. The fact that there was granite here indicates that the temperature nearby was very high. Granite is actually melts at around 700 degrees Celsius. That's well over 1,000 degrees Fahrenheit. So this was really hot stuff. There are two ways to get these granite veins here. One is to have the granite formed somewhere else and squeezed in along little cracks. The other way is to make the granite in place by actually melting some of this rock. And there is a way to decide which it is. In order to melt the rock, you have to get this up at least to 700 degrees Celsius, well over 1,000 degrees Fahrenheit. And if you do that, muscovite mica becomes unstable. This rock is full of muscovite mica. Therefore, that's not how it happened, because it was not heated that high. Instead, we formed the granite somewhere else and pushed it in here. While or after it was pushed in, this rock was heavily deformed, because you can see that the veins themselves wiggle around here in a very, very complicated pattern. This is called ptigmatic folding, and it indicates that this rock was very, very plastic, that it was almost flowing like a liquid. It was solid, but like glacier ice, solids can flow very nicely. So this is towards the upper end of the medium spectrum. This rock is medium well done. Not completely well done because the mica is still stable. But this is some really spectacular vein folding here. Yeah. As well as the granite veins that we saw running up through there, we also have this big, thick white mass in here that runs all the way up the outcrop. This is a quartz vein. It has a slightly different origin. It did not come in as molten rock. Quartz melts at a fantastically high temperature, much higher than this rock shows any signs of ever having been at. This rock was brought in by hot water solution that came in through the cracks after everything else was done. It's not so tightly folded as the other, so it probably came in after much of the deformation as this rock was cooling. This is very common in metamorphic rocks, that as it cools, quartz-bearing hot water solutions will come in and deposit the quartz as it cools. Extremely hot water will dissolve and then deposit almost anything. So that's how you get the quartz here.